next we have the Nernst equation. The Nernst equation which gives the relationship between the E and E naught cell. For example, suppose if I carry out any reaction or any electrogenesis process, and during that process if the concentration of the solution was not 1 molar, then in that case whatever the cell potential I will get, it will be nothing but E cell, because the condition because the whole process was not done under a standard condition, that is because the concentration was not 1 molar. So in that case, if you wanted to know the E naught cell value, then there is a two way for getting a E naught cell value, that is either you perform the whole experiment again by replacing that particular solution with 1 molar concentrated solution, or second method I will say directly use Nernst equation. The Nernst equation will give you directly the value for the E naught cell. So that E and E naught cell, the relationship between E and E naught cell is given by the Nernst equation. So we have Nernst equation. The equation is E is equal to E naught cell or E naught minus RT upon NF ln Q, where ln stand for the exponential log, or I can say the natural log, that is a log to the base E. What is Q? Q is called as a quotient of a reaction here. And the formula for the Q is, it's a molar concentration of product upon the molar concentration of reactant of a reaction which is taking place in a galvanic cell. But at the same time, when we write the value for the Q, that is when we consider the molar concentration of product or reactant, we only consider the concentrations of these solutions, that is aqueous ions, or the solution that is a mixture, I can say we only consider the concentration of ions. We never consider the concentration of the pure solid and pure liquid. And if there is a gas, then we consider the pressure of that gas in a reactant or product if it is present. Then finally we will have a formula, E is equal to E naught minus RT upon NF ln, instead of Q I can write it's a product concentration upon reactant concentration. Or I can say therefore E is equal to E naught minus this, if I am replacing this log to the base E by log to the with log to the base 10, then the whole expression will get multiplied by 2.303. So we will have 2.303 RT upon NF log to the base 10 molar concentration of product upon molar concentration of reactant. Now what these terms are, here E stand for the cell potential, or it may be electrode potential. If you are using the formula for an electrode, a single electrode, then E will represent the electrode potential, E naught will represent the standard electrode potential. And if you are considering the formula for the cell, then E will be called as a cell potential and E naught will be called as a standard cell potential. R is a gas constant whose value is 8.314. T is the temperature. Since we are considering the standard condition, that's why the temperature value is going to be 298 Kelvin. N is the number of moles of electron which is exchanged during the reaction, because as I said in the beginning only that in electrochemistry we consider the redox reaction only, where there is a gain and loss of electrons. So whatever the number of electron is gained or lost is always same. So N is that number of electron. F is a Faraday of electricity, and 1 Faraday is again equal to the 96,500 coulomb, that is a charge on 1 mole of electron, and product upon reactant concentration. Here as I said, E, it is nothing but electrode potential you can say, or we can call it as a cell potential depending on whether we are using a formula for a single electrode or for electrode cell. Similarly, it will be a standard electrode or standard cell potential. R is a constant as I said, so we will have E is equal to E naught minus 2.303. R is a gas constant, its value is 8.314. Temperature, standard condition we are considering, so temperature is going to be 298 upon N into 1 Faraday is 96,500 coulomb into log to the base 10, I can say product concentration upon reactant concentration. Therefore, I can say that E is equal to E naught minus, on multiplying these all constant numbers, or after multiplication and division, we get 0.0592 upon N log to the base 10 molar concentration of product upon molar concentration of reactant. So this is a Nernst equation which we use for solving the numericals when it comes on E and E naught cell. Okay. Now let us use the Nernst equation for a Daniell cell. The Daniell cell, where the electrode, the cell representation is zinc 2 plus ion concentration, whose concentration is 1 molar, then copper 2 plus 1 molar solution, and then copper solid state. Okay, now just I wanted to write the cell, that Nernst equation for this Daniell cell. So if you want the Nernst equation, then first you have to write the reaction, because here I require the product and reactant in a formula, as well as I require the value of N. So let's see the reaction taking place on anode and cathode here. Anode, that is a zinc electrode, undergoes oxidation, will give you zinc 2 plus 2 electron. Cathode, that is Cu2 plus 2 electron, will give you Cu. Add both the reactions, so that finally we will get the cell reaction. So for cell reaction, we have electron will get cancelled, and we will have zinc in solid state plus copper ion, that means it is in aqueous state, dissolved in water, which gives zinc ion again in ionic form, that is in aqueous state, and copper, it is an electrode, that is a solid state. So this is the reactant, and this is product. So let us write the Nernst equation. So here the Nernst equation will be equal to E is equal to E naught minus 0.0592 upon N. N is the number of moles of electron here. So how many electrons are gained or lost? Then two electrons are getting cancelled. That means the 2 electron is lost and 2 electron is gained. So the total electron exchange is 2. Log to the base 10 product upon reactant concentration. So product concentration, here we have two products, that is a zinc ion and copper. But as I said, we only consider the concentration of the ions. We never consider the concentration of pure solid or pure liquid. So here the copper electrode is a pure copper and it is in solid state. So its concentration will not be considered. So here only the concentration of zinc ion upon the concentration of copper ion. Again, the zinc in solid state will not be considered. So here it's we are writing for the cell, so E naught cell. So E cell is equal to the formula will E naught cell on division, this log to the base 10 concentration of zinc 2 plus ion upon concentration of Cu2 plus ion. So this is a Nernst equation for a Daniell cell. Let's see one more example. Zinc electrode acting as an anode and this hydrogen electrode acting as a cathode. So again, for writing this Nernst equation, first I require the whole reaction, that is a cell reaction. So reaction taking place on anode. So reaction taking place on anode is zinc oxidation, that is zinc gives zinc 2 plus 2 electrons. Then reaction taking place on cathode. Here it is H plus ion will gain electron, will give hydrogen gas. Since it's H2, so 2H plus 2 electron, in aqueous state it is. For getting a cell reaction, add both reactions. So on adding, these 2 electrons will get cancelled and we will have zinc in solid state plus 2H plus ion in aqueous state gives zinc 2 plus in aqueous form plus H2 in a gaseous state. The Nernst equation, E is equal to, for cell, so E cell is equal to E naught cell minus 0.0592 upon N log to the base 10 molar concentration of product. The product is here zinc ion as well as the pressure of hydrogen gas. As I said, if there is any gas, then its pressure is also considered. So here both the reactants will be considered upon the concentration of only H plus ion, and if there is any coefficients, then that coefficient is always raised to power. So here the H plus is having a coefficient 2, so it will be H plus ion square. So this will, and here N value is 2. So this is for the second one. Third, suppose if I have an electrode, only a single electrode, like nickel 2 plus 1 molar concentration and nickel in solid state. Then its reaction is going to be Ni2 plus 2 electron will give you nickel. Single electrode, so there will be either reduction or oxidation. If it is in the form of Ni2 plus and Ni, then it's a reduction, and if the electrode is given in the form of Ni and Ni2 plus, then we have to write the oxidation reaction. So in this case now, E, it's a electrode potential. So instead of cell, I will write EL, that is E naught EL, that is electrode potential, minus 0.0592. Total electron gain or lost is 2 here. The 2 electrons are involved. Log to the base 10. Molar concentration of product. There is a no ions in a product, no ions or a gas on a product side. So 1 upon the concentration of Ni2 plus. So in this way, we use the Nernst equation for a electrode or for a cell. So this is about the Nernst equation, which gives the finally relationship between the E cell and that is which gives a relationship between the cell potential and standard cell potential, or between the electrode potential and standard electrode potential. The next we have to determine the relationship between the Gibbs energy, that is the delta G or the delta G, which tells us about the spontaneity of the reaction, I can say. So we have to write the relationship between the Gibbs energy and the cell potential. So now let's see, that means ultimately we have to make a formula between the delta G and between the E cell. So for this, now in case of in case of galvanic cell, when some chemical reactions are going on, then during a chemical reaction some electrical work takes place. So according to electrochemical, means when I'm considering the electrochemistry concept, then it says that the work done or that electrical work done during the processes are nothing but the product of the cell potential and the amount of electricity passed through it. That is, the electrical work done during a reaction or in a galvanic cell is a product of the cell potential and the amount of electricity. So amount of electricity, that is a charge passed through the cell or generated in a cell into the cell potential. Now amount of electricity depends upon that how many moles of electrons is transferred during the reaction. If there is a 1 mole of electron is transferred, that means 1 Faraday of electricity. If there is a 2 moles of electron, that is a 2 Faraday. If there is a n moles of electron, then amount of electricity will be Nf, that is n Faraday. Into cell potential is represented by E cell. So on the basis of the electrochemistry concept, I can say that electrical work done is nothing but the product of E cell and Nf. But when we use the thermodynamic concept, then according to thermodynamic concept, the work is nothing but the mode by which the system and surrounding exchange their energy. Means it's nothing but the energy. So according to the thermodynamic, the galvanic cell is working. Then if the galvanic cell is working, that means it is losing some form of energy, and it loses the energy in the form of, means it loses some energy, and so that the electrical work done is always equal to the decrease in Gibbs energy. Means if you wanted to know how much work has taken place during the electrogenesis, then it is equivalent to the decrease in Gibbs energy. Gibbs energy, that is decrease, that is a change. Decrease, that is a delta G is negative. So this is equation number 2. Both are the formulas for the electrical work. So from 1 and 2 I can say that minus delta G is equal to NFE cell, or I can say delta G is equal to minus NFE cell. The first. Or suppose if I am considering standard Gibbs energy, then delta G naught is equal to minus NFE naught cell. Means if you are considering a standard Gibbs energy, then standard Gibbs energy formula involve the standard cell potential. Now here from this formula, so this gives the relationship between the Gibbs energy and E cell. Means if you know the cell potential, then simply you can calculate the Gibbs energy by using this formula. Depending on which type of energy, which energy you want, standard Gibbs energy or just a Gibbs energy, then accordingly you have to use formula. Now from this formula, I can say that, as I said in the beginning, that the Gibbs energy help us to decide spontaneity of the reaction. So I can say that for a spontaneous process, the delta G is negative. And if the delta G is negative, then minus minus will get cancelled, and so that I can say that E cell is positive. So E cell is positive. Then here the second very important point is that here if you make a formula for the E naught cell or E cell, then E cell formula will be delta G upon NF, I can say. Suppose if I am multiplying, there is some reaction, and if I am multiplying that reaction by 2, then Gibbs energy, being an extensive property, will also get multiplied by 2. And if you are multiplying the reaction by 2, that means the number of electron will also get multiplied by 2. That means if you are doubling or halving the reaction, then delta G also get doubles and the number of electron also get doubles. So here I can say that if I am doubling, then it will become 2 delta G and 2 NF cell, 2 NF, and 2 will get cancelled, means E cell will be same. That means if you are doubling the reaction, the delta G changes, the number of electron also changes. But since both changes, therefore E cell value does not change. And since E cell value does not change, therefore I can say that E cell is an intensive property. Because if I am doubling the reaction, that means I am changing the amount of a matter, and on changing the amount of matter, the E cell value does not change. Therefore, a very important point that E cell or E naught cell is an intensive property. Then the next we have the relationship between equilibrium constant or cell potential, standard cell potential. And Gibbs energy. Sorry, it's not a Gibbs energy, standard cell potential and equilibrium constant. Equilibrium constant, that is K. So the relationship between the cell potential and equilibrium constant. Now here I can say the delta G. We got a formula for the delta G, that delta G naught is equal to minus NFE naught cell. We got this, we just derived this formula, that delta G naught is equal to minus NFE naught cell. In thermodynamics, we have learned one more formula for the delta G naught, that it is equal to minus RT ln K. In thermodynamics, we have a relationship between the Gibbs energy and standard Gibbs energy, that delta G is equal to delta G naught plus RT ln K. And if I am considering a equilibrium state, then delta G becomes 0, and so that delta G naught becomes equal to minus RT ln K. So we are using the same relation here. So since both are the values of the delta G naught, so from both the equation I can say that minus NF E naught cell is equal to minus RT ln K, minus cancel. So finally we will have E naught cell is equal to RT upon NF ln K, where K is the equilibrium constant. So I can say that E naught cell is equal to R 2.303 RT upon NF, and once I multiplied by 2.303, that is ln will become log to the base 10 K. Therefore, I can say that E naught cell is equal to, here I know the values of many terms, that is 2.303, R it is 8.314, temperature we are considering standard cell, potential so 298, and into 96,500. The same values was in the case in Nernst equation also, so on multiplying and dividing you will get a number. E naught cell is equal to 0.0592 upon n log to the base 10 K. So this is the relationship between the E naught cell and equilibrium constant, that is E naught cell is equal to 0.0592 upon n log of K. So this gives a relationship between the E naught cell, means suppose if they are asking the equilibrium constant, the question on equilibrium constant, then we are going to use this formula, and if the question involves a Gibbs energy and they are asking cell potential, then we are going to use this formula.